Maybe we shall make a start.
Yeah, we can start.
Great. Hello, everyone. Welcome to the IVM seminar. And it's a great pleasure to have our speaker today, Dr. Paolo Bruzzese. He's a postdoctoral researcher at the Max Planck Institute for the Chemical and Energy Conversion. He received his PhD through a joint program between University of Leipzig and the University of Turin, and his work focuses on identifying and characterizing the active sites in catalytic material using advanced EPR spectroscopy and quantum chemical modeling. And today he will be sharing with us 017 hyperfine spectroscopy of transition metal ions on oxide surfaces. Whenever you're ready, Paolo, feel free to start.
Okay, thanks a lot for the kind introduction and for the invitation also for this very nice series of seminars, which I find super interesting and useful for the APR community, especially the young ones. And so considering the format of these seminars, which are more informal and more didactical, I can say, I decided to prepare kind of vademecum about 017 hyperfine spectroscopy in oxide materials based on my past experience in my PhD time. And the idea is today actually to discuss a bit about the potentials of using 017 labeling in solid state material and therefore the hyperfine techniques by focusing mainly on two crucial points, which are the choice of operational microwave frequency and also the choice of the experimental techniques, because I think that these are two crucial points for every EPR spectroscopist when he starts to plan or he decide to perform a specific kind of measurement on a specific system. So it's worth to be discussed. And I'm not going to provide an exhaustive review of all the possible 017 EPR literature that we can find. But I'd rather prefer to highlight the potentials and also the drawbacks of applying different approaches by selecting few examples from the literature and also from my experience. Okay, and so we can start by asking why we can focus on metal ions supported on oxides, where they are everywhere basically. So they are of key technological interest across a widespread different area like material science or sensors, energy production, or also heterogeneous catalysis. So I'm pretty much sure that you are familiar with the examples I reported here, like perovskites that have gotten big interest in the last decades, or titania, very important in photocatalysis, also in even more than 2 or 3 decades ago, and metal doped zeolites, which are extremely important in heterogeneous catalysis. The main point is that many of the questions involving these materials are arising about the understanding of the metal-oxygen bond. So the bond that the surface-bound metal species is generating through the interface with the surface, okay? And in this case, we can think that our support is not just an inert surface, but it's clearly affecting the atomic levels of our surface-bound metal species, therefore a rearrangement of our metal levels, exactly as it happens in classical coordination chemistry, where our ligand is a molecule. Okay, but in the case of a solid state ligand, then we can think that our metal species is interacting with the surface, and depending on how the interaction occurs, then it's creating bonds at the interface that can have either a weak interaction, and this is usually due to polarization effects or just weak dispersion forces between the surface and the metal species, or we can generate a covalent bond where we have a real mixing between the metal orbitals and the orbitals of the oxygen ions or donor atoms on the surface, or we can have a ionic bond where we have a electron transfer bonding situation. In this case, so in all of this case, it's fundamental that the oxygen donor atoms or ions in our surface are playing a crucial role in defining the electronic properties. And this means that we need to focus in understanding how the metal-oxygen bonding is behaving in this case, because behind the metal-oxygen bonding, we have all the informations that we know to understand how the geometric structure is, for example, occurring, or which level of covalency or on the other hand, ionicity we can have in the bonding, and also in the case, of course, of paramagnetic species, which is the case that we are all interested here, spin delocalization effect. Okay. Therefore, all these informations can be obtained at once if we target the oxygen nucleus. Okay, but we need to target the only magnetic isotope of oxygen, which is oxygen-17. Which, as you know, its natural abundance is extremely low, and therefore we need to, first of all, find ways to enrich our support, our oxide support. We need to find protocols to enrich our support, and this can be actually quite expensive for polycrystalline materials, especially if we start from a bulk synthesis where we use isotopic reactants to synthesize our matrix. But on the other hand, compared, for example, to O17 NMR, where we need a quantitative, we can say, and also a uniform, more than quantitative, substitution of O17 in the oxide matrix, for EPR we can be selective and, for example, focus only nearby, in the area nearby the paramagnetic species. And concerning oxide materials, we can distinguish between two different ways of enriching our matrix. So for non-reducible oxides, which are usually alumina, zeolites, or alkali earth metal oxides, we can use water 17 as isotope carriers, and by doing several hydration or dehydration cycles using vapors of water 17, then we can enrich and substitute. So the O16 with O17 nuclei, especially on the most reactive surface sites of our oxide materials. This means that in the case, for example, of magnesium oxide, so an alkali earth metal oxide, we are mainly enriching the corners or the edges of our system. While, for example, in zeolites, which are aluminum silicates, we are targeting mainly silicon-oxygen aluminum bridge, which are the most reactive ones, and then also silicon-oxygen silicon bridges. And this, specifically in the case of zeolites, is quite important because we know that the metal sites are usually binding around silicon, oxygen, aluminum sites, because these are the exchangeable sites in the zeolite. So we have a way to fundamentally enrich oxygen nuclei that are close to the metal center. In the case of reducible oxides, and this means, for example, titanium, we can exploit the fact that the oxygen nuclei in the surface are quite labile if we work under thermal treatment under vacuum. And so we can generate, by heating up oxygen vacancy on the surface. And then by heating up again in the presence of oxygen-17 atmosphere, we can replenish these vacancies with oxygen-17. And this is again a selective isotopic enrichment, because we are mainly enriching the surface of our titanium, which is also the most reactive part if we want to think about catalysis for catalysis. So these are the two main protocols that can be used for different classes of oxide materials. But from a practical point of view, the equipment is not super expensive or doesn't require a lot of effort. So it's important to have a EPR cell that can be connected to a vacuum line, where all the thermal activation procedure and then isotopic enrichment can be performed using either oxygen, bimolecular oxygen 17 as isotope carrier, or water 17 as isotope carrier. Then once our treatments are finished, so we have our enriched sample, it's of course fundamental to avoid that the sample goes again in contact with external agents like air or water, because we need to keep the sample in this state. And this means that these procedures are practical and can be applied for X and Q bend tube, where we can quite practically seal the tube and avoid that this goes in contact with oxygen or water. While on the other end, it can be a bit impractical for W-band capillaries, due to the fact that in W-band frequency we use very small capillaries with a diameter of usually 0.6 millimeter. And we are going to go back to this topic in the next slides when we talk about hyperfine techniques that we can use. Okay, usually another part of my research that is always combining with EPR, and in this case is also fitting very well with O17 hyperfine techniques, because as you will see, the information that we can get from the O17 hyperfine interaction is very sensitive to structural parameters, is to use also quantum chemical calculation for translating what we measure from EPR in atomistic structure, okay? And this can be done because what we fit using a spin-Hamiltonian formalism and what we obtain as a EPR parameters that can fit our experimental spectra is also connected to our Born-Oppenheimer Hamiltonian, which is the full Hamiltonian that describes the atomic structure as well as the electronic structure of our microscopic species, and therefore this can be also directly used to calculate the EPR parameters and then create a bond between structure and spectroscopy directly. in the case of oxide materials, we need to do this if we want to use quantum chemical calculations, and I strongly suggest to use them. We need to do it for a periodic system. And this is creating just one step more, because we need to optimize the structure using periodic boundary conditions. This is most favorable because we can provide a better description of the crystalline environment of our system. And in this case, in this sense, we can use hybrid DFT level of theory with some dispersion correction to account for weak interactions. And at that point, once we have our relaxed structure, then we can choose two ways. Either we continue in a periodic model and we calculate our EPR parameters within our periodic model, which has the advantage that we don't need to modify basically the model. But two big problems are that, for example, we don't have in many periodic codes the possibility to calculate G-tensor or zero-field splitting tensor in the case that we want to know also for high-spin system. And the other major drawback is that we cannot go higher than DFT level usually, which can be a problem for especially the EPR parameters related to the transition ion. Okay. And therefore, we can use the second way, which is the one that I like most, which is cutting a cluster model from the optimized periodic structure and saturating the dangling bots with hydrogen, for example. And then we can exploit the fact that the EPR properties that we are interested in are usually quite local. So without re-optimizing again the structure, we can already get a good agreement in this way with the cluster approach. And the advantage are that we can get the G and the zero-field splitting calculation in this sense, and we can usually go higher in level of theory, which is nowadays possible also without spending too much time on waiting for the result. And it's very important for the metal ion EPR parameters. Okay, so using higher level of theory like CASSF or couple cluster single double nowadays can really be rewarding. The only problem is that we need to pay attention to the charge multiplicity of the model, because this needs to be as close as possible to what we optimize in the periodic structure before. Okay, so after saying this, today I'm going to show mainly examples from zeolites, so from one class of metal ion supported oxide materials. First of all, because they are quite important in heterogeneous catalysis, and secondly, because they are quite versatile in the sense that we can use them as a support for hosting very different transition metal ions with very different electronic configuration and complementary properties. Okay, and usually the metal ions dispersed in a aluminum silicate framework like this one are allocating inside the pores or the channels of the framework, so they occupy extra framework position, and usually they stay close to aluminum sites, because these aluminum sites, these violet balls here, are basically substituting silicon sites. They introduce a negative charge that needs to be compensated by cations, extra framework cations, that in this case represents our paramagnetic species. And for example, with ion exchange procedure with copper salts, we can obtain copper 2 binding sites in 2 aluminum sites, which usually assume a distorted tetragonal geometry, or using, for example, evaporation of vanadium precursor, we can obtain vanadium 4 as vanadil in zeolites binding 2 aluminum sites like copper, or with more let's say exotic procedure, we can obtain also zinc 1 paramagnetic centers inside the zeolites that are binding in 1 aluminum sites. And in this case, these zinc 1 species are quite particular because they can be stabilized in the zeolitic framework, while in a molecular world, they are very difficult to obtain, for example. Okay, so now we can go fully into the spectroscopy of oxygen-17. This slide is just to briefly remind how the spin system looks like when we have a 1 unpaired electron coupled to oxygen-17 nucleus. Since our nuclear spin for O17 is 5-half, we have a total of 12 energy levels, so 6 energy levels for each electron spin manifold. And then we need to take in account also that we have a non-zero quadrupolar interaction that is shifting the final energy levels, which are not shifted, are not evenly shifted, but the difference in energy is proportional to mi to the power of 2. This means that in the simplest case, when we have 1 unpaired electron to coupled to 1 O17 nucleus, then we are expecting 6 lines in a hypothetical CW EPR pattern with equal intensities. Okay. In the moment in which we have 2, for example, magnetic equivalent of 17 nuclei, then we are expecting 11 lines with relative intensities that is obeying already the Pascal's triangle. Okay, and so far so good. But if we have a mixture of isotopomers, as we can call them, because maybe our enrichment level is not full. We have maybe some species with coupled to 1 oxygen and some with 2 oxygen, 2 magnetic equivalent oxygen. Then our spectrum will be a superposition of subspectra that are with relative intensities that depends on the ratio of our isotopomers in the system. And this is exactly the first case that we can expect and that I want to present now for zinc doped in zeolites. Okay, so when the zinc doped in zeolites can assume this kind of configuration, which is which we can simplify as a C2V geometry, where the zinc is binding to oxygen donor atoms across 1 aluminum sites in the zeolite, and as a peculiar ground state, which is a 4s1 ground state. Okay. So if we take a look to the CW EPR spectrum of this guy in X band and in Q band, we see that we can resolve the anisotropy of the G tensor only in Q band, where we see clearly the slightly wrong visity of the G tensor. when we enrich the framework and we repeat the same kind of measurement, then we obtain with a spectrum where the O17 splittings are kind of visible. And if we count the lines, we can see that there are mainly 11 lines that are overimposed to the central line that is coming from the non-labeled sample. Okay, so this is already suggesting that our zinc is coupled with two magnetically equivalent O17 nuclei. But in this fortunate case where we can already resolve the O17 splittings from CW spectrum, we can also use our EPR data to estimate the level of enrichment around the metal center, okay, by using spectral simulation, because we can simulate the three isotopomers cases and see which one is fitting better the experimental spectrum. And as you can see, in this case, we have a better agreement when there is a 70% of enrichment. So we can say that with the protocol that I described earlier, we can enrich, in this case, 70% of the oxidic framework. But of course, to do this, it's important to have a very good estimation of the O17 tensor, okay? And in most of the cases, the situation is different. So for example, if we take a look to copper instead of zinc, which is a D9, so we have our unpaired electron in the 3D x square minus y square orbital. Here is how it looks like the typical copper EPR pattern in a tetragonal configuration, okay? And also inside the zeolites is looking like this. But when we enrich the framework, then we don't have enough resolution to resolve, in this case, the O17 splitting. So in this case, we just see a broadening, an increasing broadening of the line, probably due to the quadruple coupling of the O17 nuclei. And we are forced to, or anyway, we cannot use a straightforward CW experiment to determine the level of enrichment and also or the small details that are hidden in the homogeneous broadening. And therefore, we need to use hyperfine techniques. And in this sense, this is the arsenal of techniques that we can use mainly to study O17 nuclei. And I will mainly focus on ESIM and mainly more specifically in high-score techniques and ENDOR. I don't have any example concerning DNMR, and I will also explain this late, but it's important to say that also DNMR has been applied successfully, especially in W-band frequency, to detect O17 hyperfine couplings here, actually in the Max Planck for chemical energy conversion. And therefore, it's also quite useful, especially when our relaxation times are not favorable enough to use ENDOR or ESIM techniques. Okay. After saying this, if we go back to the zinc and we start to classify two scenarios possible. So one where we have large O17 hyperfine couplings, like in the case of zinc. And in this case, we can already take a look to the spin density, to the calculated spin density plot, and see that there is a non-negligible covalency that is going to the oxygen that are directly bound the zinc ions, and also something on the oxygen from second coordination sphere, which is not totally, it was not totally expected if we think about the charge nature of zinc 1. This is clearly reflecting in the Davis-Endor spectra of this paramagnetic species. And here it's reported the experimental spectrum in Q-band together with the corresponding simulation at different microwave frequencies. So we can see that the Q-band spectrum is characterized by two broad peaks that are separated by twice the Larmor frequency and center at half of the hyperfine tensor. Okay, the asymmetry of the peaks is related to the anisotropy of the O17 hyperfine tensor, while the broadening is due mainly to the quadrupole coupling of the O17 nucleus. And here we can see that if we do the experiment at X-band, then the fact that the Larmor frequency is becoming very small makes that is provoking the fact that the two transitions, the two MS transitions are collapsing together, giving a spectrum that is not resolved, so that is not useful for extracting our O17 hyperfine tensor. If on the other hand, if we go to high frequency, of course, is advantageous because we get a larger frequency, so we separate better the two peaks. But one of the MS manifold is falling at very low frequency, which is usually not super sensitive as we move in a higher frequency range with the setup that we usually use in our spectrometers. And therefore, in this sense, we can see that the Q-band frequency represents the best compromise for detecting this O17 hyperfine coupling that are arising around 50 megahertz for the isotropic component. Okay. The sign here was obtained from DFT calculations, and the fact that we have this large isotropic coupling is suggesting that we have a sigma bonding interaction between the zinc and the oxygen donor atoms. Okay. So complementary, if we take a look to the I-score spectra, always recorded at Q-band for the zinc dot material, then we can realize that we get also additional information, because if we take a look to the minus plus quadrant, we get exactly the same hyperfine coupling that we have that we detected in Endor, so the large hyperfine coupling. While in the plus plus quadrant, we have also couplings in the weak coupling regime that are amenable to around 9 megahertz, and they can be assigned to oxygen from second or third coordination spheres around the zinc. Okay, so in this sense, we can clearly say that for this kind of sigma bonding situation, Endor and I-score provide complementary information, where Endor are suited for the larger coupling coming from the oxygen directly bound to the zinc, and I-score can provide information also to smaller coupling from oxygen in the second and third coordination sphere. And a similar situation can happen in the case of copper, where we also have a sigma bonding interaction, but in this case, the degree of the localization is even larger. So we have an experimentally determined spin delocalization of 30% over the oxygen donor atoms. And this is clearly reflected again in the Endor spectra that we can measure in this case, where it is possible to identify 2 oxygen species with hyperfine coupling about, for the isotropic component, about 50 megahertz and 40 megahertz. And thanks to quantum chemical calculation, it has been possible to assign these 2 oxygen species to 2 pairs of magnetically equivalent oxygen nuclei directly bound to copper. Again, if we try to see what happens if we do this experiment, not in Q-band, but in X-band, the situation is even worse compared to the case of zinc, because now we have 2 oxygen species strongly coupled that overlap all together in this frequency region, making the interpretation of the spectrum very difficult. Okay, so again, Q-band frequency represents the optimal compromise to get information on the oxygen local environment. And then we can even go farther and exploit the power of quantum chemical calculations, because in this case, if we calculate how the oxygen hyperfine couplings variate when we change the aluminum distributions around the copper center, and we compare these values to what we obtain experimentally, then we can also see that our experimental hyperfine couplings are sensitive also to tiny geometrical differences, like the sighting of aluminum around the copper. Okay, and we can also try to give a guess on which distribution is better fitting with our experimental data, and also considering energetical numbers, and try to give a guess of which aluminum distribution is the most likely representative in our sample. Okay, so a complementary scenario is represented by the case of vanadium. Okay, so in this case, we are speaking about vanadium 4. So only 1 d electron, which is occupying the 3d xy orbital. And this is an electronic configuration which is exactly complementary to the copper. So this is why this is a nice case to compare. And here we can see that the CW spectrum, okay, is giving the typical pattern for vanadium, where 1 unpaired electron is interacting with the nuclear spin of vanadium, which is 7.5. So we obtain our 8 lines pattern. And the unlabeled and enriched pattern are virtually not distinguishable. So this is already suggesting that we can expect small hyperfine couplings from the oxygen donor atoms that are not visible in the CW spectrum. And indeed, if we use I-score for in this case at Q-band, then we can get a straightforward interpretation of the entity of our oxygen 17 hyperfine coupling. Okay, which in this case is amounting about 5 megahertz for the A-iso. And in Q-band, again, we have a simpler interpretation of our O17 tensor, so we can immediately extract it. But if we compare, for example, in X-band case, then we need to look at the other quadrant again, so the minus plus quadrant. So our couplings are in a strong coupling regime. And this makes the situation a bit more complicated also because we have a double quantum transitions that are present and falling around 11 and -3 megahertz or -11 and 3 megahertz. And then we need to dig in the low frequency region to find the single quantum transition. Okay. So again, Cuban frequency is revealed to be more representative and simpler to interpret the results for small O17 hyperfine couplings. It's also important to notice that in this case, the spin density on the oxygen is only 5%. And this is clearly characteristic of a metal-oxygen pi bonding, where we don't have a good overlap between the d metal and the oxygen orbitals. And also the fact that our AISO, our calculated AISO, is positive compared to the other case when it was negative. And this is due to the fact that if we take a look to the calculated spin density, we see that the sp orbital that are direct from the oxygen that are aligned along the vanadium oxygen bonds have a negative sign compared to the 3D orbitals. And this is due to a direct spin polarization effect from the 2p orbital that are perpendicular to the VO bond, which is basically giving a negative spin density on the s orbitals. And therefore, when we talk about sp hybrid orbitals, we have a negative spin density coming from the s contribution. Okay. And so with this, I would like to give a summary saying that it's possible using specific protocols for enrichment of the oxide materials to selectively enrich the oxide materials and especially around and nearby the metal species. And we have seen that the O17 hyperfine couplings in oxide-based material can vary up to 1 order of magnitude, depending on the nature of the interaction between the metal species and the oxygen donor atoms. And we can say that while I-score is particularly suitable at Cuban frequency for detecting small, we can say small hyperfine couplings around in the range of 2 to 10 megahertz. Davis and Endor are at the same time suited to detect large hyperfine couplings, which are particular and characteristic of sigma bonding situation. And on the same time, the use of high frequency is auspicable because we can, apart from reducing the quadruple broadening, also increase the orientational selectivity. The only drawback can be the loss of signal because of the G anisotropy that is much larger in W band. And in this case, the problem was also the air sensitivity of the samples after the treatment that can be problematic when we use small capillaries like in W band. Okay. And with this, I would like to thank my group leader, Alexander Schnegg, and all my colleagues, and also my previous group in Torino, so Mario and all the other colleagues for the amazing experience there, and you for your kind attention. Thanks.
Thank you very much, Paolo, for this very nice talk. Not only several very interesting examples, but also a very good tutorial about how to use O17 labeling, how to choose the experiments, and how to do the modeling and so on. So we're open for questions now. And if you have any question, feel free to raise your hand and or just type in the chat. So I can start with a very naive question. So how generalizable is the O17 approach? I mean, so can we extend it to most of the different metals and with different spin states and orbital configurations. You mentioned there are different strategies for reducible oxide and non-reducible one. So does it mean as long as we choose the correct strategy, so we can use it to any system?
Yeah, I think so. So the point is to understand first of all which kind of oxide matrix you are dealing with.
Okay.
So it's important, and because, for example, in titania, then you can probe the titanium, which is in framework position, while in zeolite we have metals that are extra framework position. So this is not really a big deal. The problem is just to understand the liability of the oxide matrix, and then use one isotope carriers instead of the other one, and get a selective enrichment.
Okay, great. Thank you. So Alexander?
Yes, can you hear me?
Yeah.
So very nice talk. Thank you very much. So I
Thanks.
noticed your Q-band indoor spectra, you did some very nice simulations, and the peaks were very well simulated, even the line shapes, but the intensity not quite as well. Is there a reason that this didn't happen?
Yeah, I think the reason is due to some enhancement effects that are not always taken account with the simulation in easy spin. Also because usually with easy spin, I use the salt function, which is actually for CW Endor, while all the experiments that we do are usually pulse Endor. So there are some effects that are not taken account with the simulation program, and I think for this reason it's always difficult to get the right intensity with the simulation.
That makes sense. Thank you.
Thank you.
Is there any other question? Great talk. I have 3 questions. The first one is, when you did the simulation for the Endor at W band, what temperature did you assume? Can you comment on that?
Yeah, I assume the same temperature as in the experimental Q-band spectrum.
Right, okay. And the second one is, what level of DFT post-HF calculations did you use to obtain the hyperfine minus 50 megahertz?
Okay, no, so in this case for oxygen donor, for oxygen hyperfine coupling, I use DFT, hybrid DFT level of theory, because the result was already agreeing very well with the experimental values. But for other more tricky cases, where, for example, the DFT level is not able to, or it's considering your bond too much covalent, like for example, if you have a copper hydroxide or in general a metal hydroxide, in this case, it's better to use couple cluster single double level of theory at least, so you can get a proper description of the bond, of the nature of the bond, and this can give you at the end a proper and a more accurate agreement with the experimental values.
Okay. And the third question is, what about doing the experiments at even higher fields, like 263 gigahertz? There are setups that don't need capillaries.
Yeah, that's true. Yeah, that could be a viable option. But I mean, the case that I showed for the zinc, where we have a sigma bonding interaction, when you go very high in frequency and you have an hyperfine coupling, which is around 60 or 70 megahertz, then this can lead you to lose one of the transition, because it's going to very close to the zero frequency. So it can be useful for sure when your hyperfine coupling is large, but not too large, I think.
Okay. There's one more question in the chat from Chine Xing. So have you tried iron zeolite yet? And what are the main challenges?
Yeah, no, I never worked with iron zeolites. Well, I think for iron zeolites, the challenges can be that probably you're dealing with high spin systems. So this is for sure affecting the feasibility of all the hyperfine techniques that we talked today. So
okay,
it could be more challenging. But concerning the isotopic enrichment, there would be no problems for sure. It can work.
and I see Muhammad still have a question.
Yeah, thank you very much, Paolo. Very nice
Thanks,
talk,
Lukman.
as usual. Just wondering if you would imagine that you have multiple copper sites or in the zeolites, for example, that depending on the dehydration levels, you could have more than one copper 2+ species. How sensitive your 17 oxygen approach to capture this variation of species of copper environment?
Yeah, I guess this would depend on how different the G tensor, the copper A tensor are in the CW experiment, because if we cannot resolve them properly, then we are probably exciting both of them, and we can see maybe a mixture of O17 signals in our Ender spectra. So yeah, this can be an issue as long as we cannot distinguish them properly in the CW pattern, I would say.
Thank you.
Thank you.
Another question from Jason.
Yeah. Paolo, it's a great talk. Thanks for the talk, okay?
Thanks.
Yeah.
Thanks a lot.
My question is, you are using the oxygen 17 enrichment technique to characterize the oxide surfaces. Can we use the same technique to study the surface of the lithium-ion batteries? Because recently lithium-ion batteries are very popular. Can we use the same technique to characterize some of the properties of the lithium-ion batteries, electrodes, something like that?
Yeah, I think it can be tried. It depends on which kind of support you are using in the lithium-ion batteries, and as long as we have a paramagnetic probe that can be inserted inside, then this can be feasible. I don't have a lot of knowledge about lithium oxide batteries, but I think it can be done.
Yeah, thank you. Thank you.
Great. I have one last question. So have you thought about doing some operando experiments to see like how the zeolite changes while the catalysis?
No, not really in operando, but I did some always ex situ measurements, we can say, for studying, for example, how the zeolite is changing with different hydration levels. And knowing that also water is always playing a role also in catalysis, this was also something that was, let's say, the closest stuff that I did concerning concerning in operando or in catalysis. And the problem, I think, of applying especially hyperfine techniques in these conditions is the temperature, because in operando you need to work with temperature that are characteristic of the catalytic procedure, while for this spectroscopy technique we need to go way down in temperature, otherwise we don't see anything. So
yeah, that makes sense. Okay, great. If there's no other questions, so thank you everyone again for attending, and thanks Paolo for give this excellent seminar, and I will see you maybe in a few weeks' time. Thank you all very much. Bye.
thank you again. Bye.